Byzantine failure is a type of failure in a distributed system where some of the nodes or components in the system behave in an arbitrary or malicious way, sending different or even contradictory information to different nodes. It can cause inconsistencies and conflicts in the data that different nodes have, potentially leading to incorrect decisions or outcomes. It is important to trust essential systems like financial or supply chain management systems, as these systems must continue operating correctly even if some components have failed. But there exists no sufficient BFT protocols that is sufficient in geo-scale networks, which needs to achieve low client-side latencies and high server-side throughput, because existing BFT protocols have issues with high client-side latencies, synchronous communication requirements, and limited concurrency, preventing them from being applied to large-scale networks. Our goal is to resolve these challenges and fill in this existing gap.
Our proposed solution is EZBFT. EZBFT is a leaderless consensus protocol that can tolerate Byzantine faults and provide wide area latency. EZBFT has no designated primary replica, and every replica can receive the client request and propose an order of execution for the request. The command leader is chosen to ensure optimal latency. That is, no matter where in the world the client is, the command leader it chooses will be the one closest to it. EZBFT delivers the decision in 3 communication steps from the client's point of view when there is no contention, that is, disagreements, no Byzantine failures, and synchronous communication between replicas. But when there are conflicts or faults, it takes only 2 additional steps to handle the faults and deliver the decision. The protocol's core novelty is its use of speculative execution by the replicas, where replicas assume the request it has received is correct and that all other replicas are in agreement. Using speculative execution, the replicas do not have to wait for the consensus decision to execute the command, and hence, in the absence of conflicts, the result of speculative execution is correct, and it saves a few extra communication steps for the delivery of the message. But when there are faults, the client goes through all the speculative replies to propose a final order. We can see that the client actively participates in the consensus decision. EZBFT also uses the concept of command interference to allow the replicas without any interference to make independent commit decisions, and when there is interference, it helps to break the cycle or disagreements to ensure consistency across all replicas. EZBFT uses terms such as instance spaces, instance number, owner number, dependencies, and sequence numbers to maintain consistency and total ordering. By using all these techniques, EZBFT, it provides us with a Byzantine fault-tolerant system that can handle faults and conflicts, along with providing low client-side latency and high server-side throughput.
We evaluated the existing protocols and EZBFT using 3 different categories. First, we measured which protocol would give the low client-side latency and would lower its latency with the change in the primary location. Second, we wanted the protocol that will maintain the low latency even with the increase in the connected circuits or clients. And third, we wanted to know which protocol would give the high server throughput. The proposed protocol, EZBFT, has the lowest client-side latency in comparison to existing protocols, and even with the change on the primary location, the latency is maintained low by 45% than the best primary best protocol, Jijiva. This is because of the leaderless nature of the protocol. As you can see in the figure that if we look in the Mumbai, the latency is stable with the connected circuits, where Jijiva latency shoots up when the number of connected circuits reaches 100. Lastly, the server-side throughput increases by 4 times when the client send requests continuously and asynchronously before receiving replies. This is because replicas are able to process and deliver requests concurrently. Thus, EZBFT is a better protocol than the existing primary-based protocols. Thank you.